So now for a MadAsMaths question within constant acceleration. Let's take a look at what we've got. Good question's quite short, but it is a very, in my opinion, interesting question. Okay, so the idea is you're told that something's been thrown straight up into the air. So it goes straight up and it comes straight back down again. And you're told that it launched upwards at 20 meters per second. And you know, there's a subsequent motion, and the idea is that for some amount of time that particle is going to be above a height, right? Some height h. We don't know what that height is, but you know it's above that height h for exactly 4/49 seconds. So just to put that in sort of real world terms, it's about 0.08 seconds. And then you're asked to find what is this height. So interestingly, that does have a unique answer. Okay, so all you've been told is it's thrown up in there 20 meters per second, and for 0.0816 roughly seconds, 4/49, it's going to be above a given height. What is that height? So the way we're going to do this is partly by considering the graph. Okay, that's what I would suggest. Consider the graph of what the displacement time scenario looks like for this. Okay, consider that and see how you do on this question. It's a tricky one, but see how you do. Pause the video now. Okay, so we're going to determine this value for h. So in order to do this, let's look at the displacement time graph. Okay, so I'm going to throw up my set of axes. Okay, and time, as always, is the independent variable on the x-axis, and I'm going to have my displacement here, which is s. Can I spell that? Displacement s. Okay. So what is the graph going to look like? Well, you know suvat. We know the initial speed is 20, so I'm taking up as positive. We know, well, time is the independent variable. S is the dependent variable on my graph. And what else is missing? The acceleration is going to be downwards at minus 9.8, right? That's the g, or minus g, I suppose. Okay. So therefore we have, you know, our favorite one, s equals ut 20t plus a half at squared, so that's minus 4.9 t squared. Okay, that then is actually the graph that we're going to draw here, right? Because, you know, that s is displacement and it's a function of time t. Okay, so let's draw the graph. What does it look like? In order to do that, let's think about some key values. What about when t equals 0? When t equals 0, what's s going to be equal to? Well, it's just 0. Makes sense. What else can we say? To be honest, I don't think we need to think too much about the finer details. What's more important is the shape. Okay, so let's say 0, 0 is here, and the graph is going to go up like this, and we know it's going to eventually come back down like this. So we know it's some sort of, you know, minus x squared kind of shape, right? Because it's a quadratic, the coefficient before t squared is a minus, so therefore we know it's this kind of shape. Okay, I don't know where it crosses here, but I'm not particularly fussed. Okay, now here's the thing. There's a height h somewhere on this displacement, okay, axis, let's call that h there. And if I mark h like that, then what the question's telling us is that between that point there and that point there, those two red x's I've marked, the time that it spends on this yellow part, that is the, what was the value? 4/49. That's 4/49 seconds. So graphically, the way I would show that is by saying, okay, if we then take these marks on the graph here, that length there, that is, I've forgotten it again, 4/49. Okay. So how are we going to find this h? Well, this is the way I would do it. I'm going to suggest that we give a name to these mystery values on the time axis. Let's call this T1 and let's call this T2. So T1 is the first time that the object reaches the height h, and T2 is the second time that it reaches the height h when it's on its way down. Okay. We know that this green distance that I've marked is 4/49, so that's the same thing as saying that T2 minus T1 equals 4/49, right? Because T2 is just the distance from the origin to T2, and T1 is the distance from the origin to T1. So take the difference, you get T2 minus T1 is 4/49. Right, what else can we do? Well, what we could do is get ourselves effectively a few equations out of this. Okay, we know that the graph is modelled by s equals 20t minus 4.9t squared. Let's plug in the values we've got. So when time is t1, that's 20 times t1 minus 4.9 t1 squared. We know the height, s, or displacement, is h. And similarly, it's also h at t2, so therefore we can also say this, t2 squared. If we rearrange both of these into the forms of quadratics, then let's call this, say, number 1 and number 2. Then number 1 is going to be the same as 4.9 t1 squared minus 20t1. Let me get this the right way around, plus h, oops, plus h equals 0. I'll just make a little bit more space there. Okay, that's the first equation. And the second one is similarly 4.9 t2 squared minus 20 t2 plus h equals 0. I mean, it's the same thing, right? Because the original was the same thing. So what am I doing here? What was the point of doing both of these equations? Well, actually, this is the thing. We don't really need both, okay, because they are effectively saying the same thing. Okay. Instead, let's just focus on this one. What kind of equation is this? It's a quadratic, right? So just think of it as t for a moment. Okay, and T2 and T1, okay, are going to be solutions of that equation. So just from the one equation, we're going to get our two values for T1 and T2. Okay, and we're going to do that using the quadratic formula in this case. So minus b, that's 20, plus or minus the square root of b squared, that's 400, minus 4a times c, so that's minus 4 times 4.9 times h, that's minus 19.6h, all over 2a, so that's 9.8. That is our value for the t's. Okay, and in this case then T1 is equal to the positive version and T2 is equal to the negative version, except the other way around to what I just said, because of course T1 is the smaller value and T2 is the bigger value. So let's just put this over here. We've got 20 minus for that one and 20 plus for this one. So just bear with me while I make this clear. t1 is the smaller number and t2 is the bigger number. Okay, right. And let me just neaten this h up a little bit because I think that looks a little bit unclear. Okay, so that's our capital H. Right, so we know that t2 minus t1 is 4 over 49, so therefore this time minus that time is 4 over 49, and hopefully you can see a lot of stuff is going to cancel here. If you work out t2 minus t1, I'm doing here at the bottom, I'm going to get 20 minus 20 is 0, and then the square root expression minus the square root expression again. So that's just going to give me 2 times that rooted expression, 400 minus 19.6h, and it's still all over 9.8. And that must be equal to 4 over 49 because that's t2 minus t1. Okay, so a bit of rearranging, we get the square root of 400 minus 19.6h equals, and I'm going to do 4 over 49 times 9.8 and divided by 2. So what do I get on the calculator? I'm a bit too lazy to work that out in my head. You get 0.4. 0.4. So therefore, let's clear up some space here now. I'm going to get rid of these because we don't need them anymore. We've now got this, and we're getting there. We're going to get a value for h soon. 400 minus 19.6h is equal to 0.4 squared. So we're going to have 0.16. And let's do a final bit of rearranging. Therefore, h will be equal to 400 minus 0.16 divided by 19.6. And I type that into my calculator and I get 20.4 meters. That's our value for h. Okay, so the final height is 20.4 meters. That's what this value was here the whole time, 20.4. So for exactly 4 over 49 seconds, this object is going to be above a height of 20.4. Okay, it's quite an interesting technique that's been used here. There is actually, I think, another way to do this, which doesn't involve doing the quadratic expression. So I'd be interested to know if you found another way. This way is a little bit tricky, but I think it's potentially more interesting than the alternative method of doing it, because it really gets you to think a bit carefully about how this capital H appears as a constant within a quadratic expression, and then that gives you 2 solutions which, when you deduct them from each other, cancels out quite a lot. And I suppose that's partly to do with the symmetry of this sort of motion. It's a very symmetrical sort of motion, and therefore these times are in some sense kind of symmetrical about a point, which I think in this case was well, I'll leave that to you to figure out. But there we have it. We have a height of 20.4 meters. That was our value for h.